causal inference from time series data, and I'm particularly interested in cases where we're trying to learn from observations, where we can experiment on a system, and my specific interest is doing this to improve human health. So the methods I'll talk about here are applicable, and I've applied them to political science and financial time series, but my real interest is health data. And so things like, can we understand risk factors for heart failure by analyzing electronic health records? Can we find causes of secondary injury in stroke patients? Why is a specific individual having a hypo or hyperglycemic episode? And all those sorts of things just when we're observing. Okay. So why am I focused on observational data? Oh, there should be, there, causality first. Right, so a lot of people might think, well, we have a ton of data, we can make predictions from correlations, why would we obsess about causality, which is so hard to find? But actually, I would argue, even if you're just interested in prediction, you want causal relationships. And so if we're making predictions based just on correlation, they're not really robust. We can't predict when they're going to work or when they're going to stop working. So things like Google flu, we don't really know why certain keywords are related to flu cases. Are they people with the flu and so on? And then Google flu started massively over-predicting cases of the flu, and that's because it's based on correlations. Second two are there's less argument about why we need causes. So one is explanation. I'll talk about that in the second part of the talk. If we want to understand why is a specific individual having a heart attack, it doesn't help me to know what factors are correlated with the heart attack. I need to know for this specific person what led to it. And finally, this is because we want to make decisions, right? So we want to treat patients, we want to develop public policies to prevent disease, or reduce risk factors for disease. We want to take actions such as buying stocks, selling stocks, and so on. Okay, now I'm struggling with the probabilistic clicker. So why would I do this from observational data? So the first is in the cases I'm interested in, I can't experiment. Most of these would be unethical, right? I can't give people heart failure and make them smoke. In other cases, it's infeasible. So if I want to understand what happens before people get heart failure and I want to make decisions today, I can't collect data for 40 years, right? I need to use the data that already exists. And finally, it's also really expensive to collect data from thousands of people. So we did a study on heart failure. We had data from 30,000 people in rural Pennsylvania. To collect that kind of data would be enormously expensive. And so being able to reuse existing data is a major help and lets us do studies we couldn't do otherwise. And also there's a huge amount of health data that's routinely collected that we can try to make use of. So electronic health record data, intensive care data. My group most recently is using body-worn sensor data in the outpatient setting as well. So in this talk, we'll look at, well, bad things that can happen with data, but also it's not totally hopeless and we can make some progress in getting causes from data. We should worry a little bit more than we're currently worrying about non-stationarity and missing data, and then how we can automate explanation to say why something happened. Okay. So when I say causal inference, I'm not picturing a graphical model. I'm not going to talk about the details of the methods, but just so you have a mental picture of what I mean by causal relationship, I'm really interested in time series data. And so I want to know not just smoking causes lung cancer, I want to know how long do you have to smoke to get lung cancer, right? What's the duration? When is lung cancer going to happen after you start smoking? And so with logical formulas, I can represent durations like that. I can find the probability of lung cancer after smoking for 5 years is different from the probability after 20 years. I can find how long it takes, all of that kind of stuff. And then I have 2 books on causality at different levels of technical detail. So the current one, Y, has no technical detail and is supposed to be for people maybe outside computer scientists, lay people, and takes a much broader view of causality and discusses psychology and things like that. And there are a bunch of copies. Right, so the key point is we're trying to figure out not just correlations, but causes, and we do that by assessing the significance of each relationship. And so we have a measure for causal significance that essentially tells us how informative the cause is about the effect after we account for other factors. So as I said, we're going to ignore the technical detail here. The method works. It's been compared against lots of other methods on time series data. But as I said, it's focused on just that case. I can't handle the case where we have cross-sectional data, for example. We also find the timing directly from the data. And so I don't assume that I already know what hypotheses to test or which are the right time windows to test a priori, we actually infer those in a data-driven way. And so we can actually start by, we test some candidate time windows, and then refine those from the data using a greedy search that actually provably converges to the true time windows. Okay, so the first application, before this I'd worked on understanding heart failure from electronic health records. There's a huge amount of missing data in electronic health record. Patients aren't going to the doctor every week. You have huge gaps. And so then I got involved in looking at ICU data and thought, well, this is great. It's a captive audience. You have very high frequency measurements. You're not going to have 6 months of missing data. What can we learn about stroke recovery in this setting? And on disk, my data for 98 stroke patients was the same size as data for 30,000 patients with heart failure, just for comparison. So these are really, really intensively monitored patients. And the question we had is, how do patients change over time during their stroke recovery? So we had data from 98 patients that have a particularly bad form of stroke. It has very poor outcomes. These patients were also comatose. And so for a doctor, the patient seems like a black box. They have high frequency EEG, physiologic monitoring, and so on. But these are all on disconnected monitors, and it's extremely difficult for doctors to make decisions. We had depth and surface EEG, so brain activity within the brain on the surface of the skull, microdialysis, which tells you about brain metabolism, all these sorts of things. Key limitation is we know nothing about procedures. So we have no idea what interventions are being done, what medications are being administered, what surgeries are done. So that's a major limit. The challenge there and our focus on untrustworthy timings and data is because these are recorded after the fact. And so you have no idea, if you actually use that data, whether the medication is given before or after something happens, or after you see the effect. And so completely useless for causal inference. Right. So there was a ton of data, which was super exciting. However, a huge amount of it was also missing, surprisingly. We sort of assumed data is recorded automatically. It's at a frequency of 5 seconds. But all sorts of things go wrong in the ICU. So there are device malfunctions. Devices are disconnected to perform a procedure. There are different monitors are started at different times. Different patients have different variables measured, all these sorts of things. And you're probably getting the picture that this data is not missing at random, right? And so the other problem is if we ignore the missingness, then there's a huge amount of bias in our causal inference, right? We might have things that are measured just for the more severely ill patients. Whether something is measured or not might tell us about a doctor's hypothesis of what's wrong with the patient, and so on. And we couldn't apply traditional imputation methods, mean mode imputation, or k-means because we had other challenges. So one is you can also have all of your data missing at a single time point, right? So if every monitor is disconnected to perform a procedure, I have 0 data at this time. There's no chance I can use k-means because I can't find similar time points since I have no data at this time point, right? So that was a major challenge. Other challenges were that the data didn't just have one type of missingness. We had all sorts of fun things. So the missingness depended on both the variable itself, so it was NMAR, and missingness also depended on other variables. So you can imagine whether blood glucose is measured and the value itself depends on measurements of blood glucose. So if the value is very high or uncertain, it might be measured more, but also depends on insulin and other things that are happening. And so there weren't existing methods that could handle both types of missingness, both in a single variable and in a single data set. And making things even more challenging, variables were also correlated across time. And so the right times to use to impute a value weren't necessarily the same time. So this is a simple example. This shows we have 3 variables, and if we want to find the value of x at time t, we should be using earlier values of time y and z, right? We don't want to use y and z at that time because x is just a lagged version of y and z. And this is really similar to what we find in a lot of cases in the ICU, except that the lags differ for all the different variables, right? There's not just one lag. We have to actually discover that. So we have a paper on this, and there's also code on GitHub for our imputation method that I'll tell you about in a second. The basic idea is we combine k-means imputation, except we now do k-means with a time lag. So instead of finding similar instances, we used lagged versions of variables, and the lag can be different for different variables. And we combine that with the Fourier transform. And so that's a super common method for imputing missing values, where the values depend on the variable itself. And so by combining these, we can now handle two different types of missingness, and also cases where we're missing all the data at a time. And part of that is using the Fourier transform, but also because we have the time lags, you'd have to be missing a large, data that includes all the time lags to not be able to find a similar instance, right? Because it doesn't depend on just the one instance, it depends on all the different instances for the variable. And the usual slide, our method does better than all the other methods. Right, sort of boring. And so the limitation of this is we simulated missingness by deleting random values up to 50% missing, and we did quite well. I said limitation is, in retrospect, I think we should have simulated the reasons for the missingness instead of deleting random values and had sort of missingness based on things like interventions and stuff like that. But it's highly accurate even with up to half the data missing. And we tested on the ICU data as well as some simulated diabetes-related data, that sort of thing. Okay, so we used this to impute the missing values in our stroke data. Going back to our causal inference, right, this was our motivating problem that we wanted to solve in the first place and then had to deal with all the data challenges. And the first challenge was, if you do causal inference here, you have different variables measured for different patients, and the patients are also extremely heterogeneous, but you have a lot of data on them. So we actually inferred separate causal models for each individual. And then further, the patients are extremely non-stationary and changing over time. So here we split the data into two different time periods that were thought to be clinically significant. In current work, we're working on actually finding transitions in the data that, change points where there's a gradual transition, where it's not like a light switch, but things are gradually changing over time. So what you're seeing here are the two different causal models we found for the two time windows, and the numbers in black are how many patients that relationship was found in, and the percentages are how many patients have the head and tail node monitored. And so one example, CPP, we found that autoregulatory relationship in 14 people, and that's 21% of it measured, because some variables are only measured in 10 people. And so it's sort of hard to compare and understand, what does it mean to find something in 10 people out of 98, right? And the interesting thing was we found that the causes of brain swelling seem to change over time during stroke recovery, and actually that more causal relationships developed later on in recovery. And now we're investigating causal relationships beyond variables. Maybe it's not the individual relationships that are important, but that homeostasis is disturbed, and then over time, new connections emerge to maintain it. Okay. So then once we know this, we have this model, now we want to use this to understand individuals, right? Why is this specific person having a seizure? Why is their brain swelling? Why is an individual having a hypo or hyperglycemic episode? Things like, what caused a stock market crash? What caused a car accident? These are all questions about causal explanation. This has been fairly ignored in computer science. We've mostly focused on learning causal structures and not doing explanation. And even more importantly, there's been very little work on automating explanation. And so there have been methods, but they require human intervention and input, and then the output can be subjective. Whereas we want this to explain in real time for a doctor, right, what's happening with this patient and why. And so just looking at the difference, it's a hard problem because what happens in a specific instance doesn't necessarily have to relate to what we already know. And so someone can have both thyroid dysfunction and uncontrolled diabetes and heart failure, but have only one of these cause their heart failure, right? It's not necessary that both the thyroid dysfunction and the diabetes are causing heart failure. And there might even be another cause that we don't know of, right, that's causing it in this specific instance. Things can work differently. A drug that normally prevents death might cause it in a specific case, all these sorts of things. There's a lot of complexity. So our goals are, first we want explanation to be completely automated. There should be no human in the loop whatsoever. we want to find causes also not just of whether or not something happens. It might be that a patient was going to die no matter what, but something caused the death to happen earlier than it otherwise would have, right? Or in other cases, so that's a cause of when something happens, not just whether or not it happens. And also a cause might not change whether or when, but might change how something happens. And so that's a cause of intensity. And so you can think of something like maybe your glucose would have risen at exactly the same time, but it went up by a lot more because of a particular cause. And so we have a paper on this at AAAI and also more code on GitHub for explanation. The basic idea is simulation of counterfactuals. And so we assume we have some model of how things normally work. It's a stochastic simulation. And then basically we take what happened in the actual world, go backwards a little bit, and then simulate forwards and toggle the cause on and off and see what happens. So here the red line is what actually happens. That's our actual world throughout time. And then we go back tau time units and then go forward. We see when we go back tau units and A is true, we mostly go through a set of worlds where B ends up happening. And when A isn't true, then we mostly end up in a set of worlds where B doesn't happen. And so using this, we can basically just compare the probabilities, right, of whether or not something happens. We simulate a number of trajectories until we reach statistical significance. We have enough samples. And then by comparing the probabilities, we can test whether or not something was a cause of whether something happened. So if it raises the probability, it's because. If it lowers, the event happened despite the cause. The same thing for timing, right? A cause can hasten or delay if the time was different. And then if we have some way of quantifying an event, whether it's a continuous valued variable or we have some other feature of it, then we can compare those values and see whether the event was attenuated or not. Okay, so you'll see, hopefully, a brief video of simulations of first the actual world and then what happens when in the counterfactual world and otherwise. Oh, maybe not. Okay. No. Oh, no bad things happen. Can you press the play button or no? It's okay if not. Okay, we'll give up on that. If you're dying to see billiard balls, you can find me during the break. I have the slides. Okay. So these are just a couple examples of the less exciting non-video output. So what did the result of our simulations look like? So this is a case we simulated billiards. We have the 7 ball hits the 8, 7 hits the 6, and 6 hits 8, and then 8 goes in the pocket. And basically we want to look at was 7 hitting 8 the cause of it going in, was 6 hitting 7, and so on. And what you see in the histogram is that we find that the cause was less reliable, but it made it happen earlier, right? So in gray, you see the timing is sooner, but the peak is lower, and so it's hastening, even though it made it less likely to happen. Whereas the other 6 hitting 8, the counterfactual, was more likely, but it would have been slower. So we actually get more information about the causal relationships versus just whether or not something happened. Our main motivation was understanding glucose and diabetes. So there's actually a really nice simulation of the insulin subsystem in humans. It's been well validated. It's not a perfect model, but it closely approximates how insulin is metabolized and glucose regulation. So we have this simulation, and what's interesting here is the true cause of an event might not be the most recent event. And so something like exercise can affect your glucose 24 hours later. And it's really, really hard for a person to figure that out, right? Because you think of the most recent event, the insulin you gave yourself, your lunch, and not what's happening, from your exercise yesterday or your illness or those sorts of things. And so our motivation was trying to develop a method that could create those explanations for a person automatically. And so here we use the simulation. We have an individual, he goes for a run, he has lunch and gives himself an insulin bolus, and we want to know, why is his glucose low? Is it his insulin bolus? Is it his run? Is it the combination? And so in the graph, you see, again, the actual world in red, And then you see what happens in the counterfactual world if he hadn't gone for a run or if he hadn't had lunch in the insulin bolus. So what you're seeing is in the blue, the run makes a huge difference, right? If he hadn't gone for a run or if he hadn't had the insulin, his glucose wouldn't have been too low. And so we can go beyond just the most recent event, right? We can find earlier and earlier causes for an effect. And we can also find out quantitatively how much of a difference it made. And so we won't talk about that here. We have results in the paper and shows how much lower his glucose was. And so it helps an individual. Ultimately, the goal is it would help an individual learn how things affect their glucose. Okay, so going back to the motivation for health, ultimately our goal is to combine the causal inference and causal explanation into an individual system. Oh, we might be missing a really exciting picture. Okay. Interesting. So we've actually been working on automated nutrition monitoring. So combining audio and motion sensors for figuring out what, when, and how much you're eating at any given time. So we have head motion, 2-wrist motion sensors, and we created an earbud for this. And the idea is, can we create a Fitbit for nutrition? And the vision is combining this with the explanation inference. And so for an individual, once we can automatically collect your nutrition information, we have physical activity monitors, we have your glucose sensor. Now I can tell you in real time how is your meal affecting you. I'm hoping that there's a picture. No. There's a super exciting confusion matrix that sadly you're not seeing. It's a beautiful confusion matrix. Find me later. It was just thrilling when it happened. But actually, so what we're showing is we have really high accuracy right now for detecting what you're eating. We have about 83% accuracy with 40 food classes. They're totally unrestricted. It's not people eating a potato chip or an apple. People eat sushi, Chipotle bowls, steak and potato, all kinds of things. And then also we can estimate how much you're eating. Right now we're at about 35% absolute relative error, which the exciting part is that's on par with human annotators. Humans annotating images are at about 33%, and human self-reports are consistently underestimated by 20%. So on the right, it's just showing there's a consistent relationship between, here it's choose after food intake and then the size of the intake, but you really need to know food type to make use of that, right? It's totally different for the steak and the potato. And so we have a system that it estimates what you're eating and then estimates how much you're eating. And the next step is incorporating the causal inference with that. But causal inference, there are many open problems, lots of things to work on. So we're currently working on inference when, as I said, the timings can't be trusted. A big open question is, what's a variable? I don't know that I have the right sets of variables. How do we discretize data? We have no idea, and it completely affects what we can find. An explanation beyond the model. So one thing here is for explanation, we assume that what we know in the model applies to what's in the real world, but maybe our model is incomplete, right? And how do we discover new explanations from our data? And then with that, I'll just thank collaborators and note that my group is hiring postdocs, programmers, and PhD students. Thank you.
Samantha, we apologize for the slide.